Welcome to Gas Law Stoichiometry. So, experiments generally do not occur at STP. Remember, STP stands for standard temperature and pressure. That's when you have 1 atmosphere of pressure and 0 degrees Celsius or 273 kelvins. So when you're using the 22.4 liters per mole, molar volume conversion factor, that only is appropriate when we're dealing with STP conditions. Like I said, most reactions don't happen that way, so this is going to be what we have to do if we don't have STP conditions. So remember, when we were dealing with gases before, our first step was to actually solve for moles. We solved for moles. Remember that with the ideal gas law, that is abbreviated with the symbol N. So in the case of this example, you have an equation where you have 3 moles of copper reacting with 8 moles of nitric acid to produce 3 moles of copper nitrate, 2 moles of nitrogen monoxide gas, and 4 moles of water. It also says that we have 4 liters of nitrogen monoxide gas, our air pressure is 1.05 atmospheres, and the temperature in the lab was 22 degrees Celsius. So based on this information, can you solve for moles with the information we've been given? And the answer is yes, because we can use something called the ideal gas law, which we learned about before. Okay? So, if we're going to use PV equals nRT, we have 1.05 as our pressure in atmospheres. We have 4 liters of nitrogen that we're generating. We do not know our number of moles. Because we have liters in atmospheres and we can convert 22 degrees Celsius to 295 kelvins, then I can use my 0.0821 R value. Remember that unit is liters times atmospheres over moles times kelvins. Okay, that whole thing was the unit. So my working equation from PV equals nRT, if I'm solving for N, is going to be PV over RT. And my plug-in for that is then going to be 1.05 times 4 divided by 0.0821. Remember, that's my universal gas constant. Times 295 kelvins. Okay? So that ends up being 0.17 moles. Of nitrogen monoxide. And actually, if I'm using appropriate sig figs, I'm going to have to squish it in here. It's 0.173 moles. Okay, so that's my N, right? That's how many moles of nitrogen monoxide I have. And in the question, I'm asking what mass of copper would we have needed in order to make that amount of nitrogen monoxide? If I have moles, I know we've done mostly mass-to-mass calculations, but if I have moles already, then I can really go ahead and switch to moles of my other thing because I have that thing such as a mole ratio. So I can put moles of nitrogen monoxide on the bottom. It's a fairly common mistake to try to use molar mass next, but that's why you need to look at your units. If you have moles of nitrogen monoxide, then you should have moles of nitrogen monoxide next in your factor label tree and not molar mass, okay? Because I don't need mass of it for anything in the question. So keeping going with what we were doing, we're trying to find how much copper we would need in order to make this, right? So I want to switch to moles of copper, and then if I have my moles of copper, I can find my grams of copper, because I can use molar mass at that point. So my mole ratio based on my balanced chemical equation is going to be 2 moles of nitrogen monoxide and 3 moles of copper. 1 mole of copper weighs 63.55 grams. So if I do my math there, again, what I'm finding is I went straight to a mole conversion because of the fact that I already found moles using the ideal gas law. Sometimes you can work the other way and you may actually need the ideal gas law first, or actually I should say you may need stoichiometry first before you use the ideal gas law. It really just depends on the question. Just like all things with chemistry, it depends on the question. But when I solve for this, I get 16.5 grams of copper. So what this means is that that's how much copper I would need to add to the reaction in order to make the amount of gas that I had desired. So when you guys are applying this to your experimental design, you're going to be starting out with your reactants, and that's basically what your next example is going to be. So I want you to just pause the video and try the example first, if you would. If you have unpaused, hopefully you have a balanced chemical equation, and hopefully that balanced equation looks kind of like this. You may have included states of matter, those could have been helpful, and if you wanted to be super correct, because it says it's being heated in a stream of gas, you would put a delta over the reaction arrow to indicate that heat is being added. But the question is asking, in this case, at what temperature was the reaction carried out if we had 13.97 grams of pure copper formed after we used up a given volume of our hydrogen gas. We also have the data for the lab as far as the pressure, just not the temperature. So in this case, I should note, if it was me, that I could use either the hydrogen gas or the water vapor and use the ideal gas law because they're both gases and I have other variables available to me. In the question, it's talking about how much volume of hydrogen gas I had. Therefore, I'm going to use that as my unknown. So if I label my equation, that's my unknown. And I do know how much copper I made. So in this case, it was 13.97 grams. Okay? So I'm going to use that known to find the amount of moles of my unknown. So that means I'm going to stop before I get to the mass of gas, the mass of the hydrogen. So I have my copper here. My molar mass of copper again is 63.55 grams. And in this case, I'm going to stop at my mole ratio because I would have 1 mole of copper on the bottom and 1 mole of hydrogen gas on top. The reason I would know to stop is because in order to use the ideal gas law, I need moles of a gas, not grams. So if I went and used molar mass, I would be doing extra work that I did not actually need to do. I would literally be doing extra steps. So when I do this, I get 0.2198 moles of H2. Okay, so that's how much hydrogen gas I am generating, or how much I needed, excuse me, to generate my 13.97 grams of copper. So if I was trying to figure out at what temperature this reaction happened, then instead of solving for N, I would be solving for T. So T, my working equation, is going to be PV over NR. And I would be using all of the data the same way I did in the previous question. But note, again, in the first question, the example that I did to start with, we were looking at finding moles and then doing stoichiometry. But in this example, we are doing stoichiometry first and then finding temperature using the ideal gas law. So we switched in which order we did those things. So for PV over NR, we said that the barometer read 1.02 atmospheres. That's an M, excuse me. I had 12.36 liters as my volume. I now know that that also corresponded to 0.2198 moles. And I still have my same R that I've been using. So remember, liters, atmospheres, moles, kelvins. Okay? And what I get there then is 698 kelvins. Okay, in the question it asks you how many degrees Celsius, so you subtract 273 and get 425. This has been Gas Law Stoichiometry. I hope that you find that helpful. Good luck on your lab that you should be attacking soon.